Hi everyone and welcome back to the channel. This is the first of two videos in which we're going to be looking at the ideal gas law. In today's video we're going to have an overview of the principles within the ideal gas law and the resulting ideal gas equation. We're also going to be applying that ideal gas equation to some practice questions involving the two most used unit combinations. In the next video, we're going to be modifying the ideal gas equation to examine other variables not included in the original equation, including density, mass, and amount in molecules. More on that later. We're also going to be looking at the conditions in which the ideal gas equation cannot be applied and how a gas that is too real could be addressed with a different equation. Okay, the first thing we should know is that the ideal gas law is essentially a product that has come as a result of combining 5 different laws. Those laws are Boyle's law, Charles's law, Avogadro's law, Gay-Lussac's law, and the combined gas law. All 5 laws examine the properties of gases and contain the variables that were combined to form the ideal gas equation. I won't be going into too much detail about these separate laws in this video. However, if you want to learn more about them in detail, please head over to my blog, the link to which I'll leave down below. Okay, so we were all probably first introduced to gases in school when we were taught about the 4 states or 4 phases of matter. That's solids, liquids, gases, and plasma. This was probably quickly followed by a simplified version of kinetic theory, where we examined the positioning and movement of particles of these states of matter, and we were able to compare them. For example, solids consist of particles that are fixed in position, closely positioned to one another, usually in a regular pattern, and we usually see that lattice diagram that is commonly used to illustrate this. Any movement is typically limited to vibration at the fixed position. In comparison, gases can move more freely, constantly traveling around in the system such as a container in random directions, usually filling the container. We also learn to assume that the particles are relatively very small compared to the large distances between them. Yet collisions between the particles do occur in addition to collisions between the particles and the surfaces or walls of a container. These assumptions within kinetic theory underpin the assumptions about the characteristics of an ideal gas, which in turn informs the principles of the ideal gas law. Okay, so what are the assumed characteristics of an ideal gas? Like I said before, gases that are examined perfectly by the ideal gas law are termed ideal gases. Ideal gases correspond with the following: that they consist of gaseous particles, thus atoms, molecules, or ions that move in constant and random motion. Now, the noble gas elements are the only gases that exist as single atoms. They have such a stable electron configuration that they can exist without having to bond with anything. On the other hand, you can have diatomic molecules, so these are 2 atoms of the same element that are covalently bonded together, or you can have gases that consist of atoms of different elements being covalently bonded together, such as carbon dioxide or hydrogen sulfide. Just as a quick reminder, covalent bonding is a form of bonding in which electrons are shared. You can have examples of gases that are ions in a gaseous state. However, it is unlikely that you will get a question in an exam or test where you must apply the ideal gas law through the ideal gas equation to a scenario involving an ionic gas. This is why all the upcoming examples and questions in this video will involve either gaseous atoms or molecules. Okay, so what other assumptions do we have? The particles have a negligible volume relative to the total volume of a system, such as a container. This refers to the idea that the system or the container is primarily empty space. The idea that those distances between those particles are so large that you can consider that any volume taken up by those particles is negligible. Now, the key word there is negligible. If you're given a question in a test or exam and you're asked to talk about the assumptions underlying the characteristics of an ideal gas, you must say that the particles have a negligible volume rather than saying very small, because when we talk about negligible, we're talking about something that is so close to zero that we can essentially discard the idea that it can take up any significant notable volume. So just a quick reminder, when you're talking about the volume of particles in regards to an ideal gas, use the term negligible. That the next principle is, or the next assumption rather, is that there are no or there negligible forces, attraction or repulsion, acting between the particles. This refers to the idea that the particles, when they move around randomly, they're not really drawn to each other. They don't really repel one another. So their existence doesn't really directly influence how the existence of other particles doesn't really influence how they move. However, they do collide with each other. But there is a key element there, a key principle rather, that needs to be remembered, that any collision between those particles, or indeed the surfaces of the container that's active in the system, is elastic. Now this refers to the idea that there is no net loss of kinetic energy. So there is no loss of energy as a result of conversion, for instance, from kinetic energy to heat. But there is also one other thing. When we do have collisions between gaseous particles and the surfaces and walls of a container acting as a system, that's pressure. When we talk about pressure, which is a fundamental variable within the ideal gas law and a component of the ideal gas equation, pressure is essentially the result of those collisions between those particles and the surfaces and the walls of a system. The final assumption refers to the idea that the absolute temperature of the gas is proportional to the average kinetic energy of the particles. So this refers to when the idea that if you have an increase in the absolute temperature of a gas, absolute temperature is obviously the temperature scale in which we measure in Kelvin rather than Celsius, and that's a key component that we must remember as well. We're talking about absolute temperature when we're talking about the ideal gas equation, ideal gas law. When there is an increase in absolute temperature of the gas, there is a proportional increase also in the average kinetic energy of the particles. These assumptions, the particles of real gases rarely comply with all these assumptions perfectly. For instance, when we talk about the idea that there can be no what we call intermolecular forces, van der Waals forces, acting between gaseous molecules, that assumption in reality is unlikely to be correct. We are going to have intermolecular forces, although they are likely to be very weak. However, the variation compared to the ideal conditions is usually small. Therefore, the ideal gas law and equation can usually be used, providing that the pressure and the temperature are reasonably ordinary. However, there are exceptions, which will be discussed in the next video. Okay, so the variables of the ideal gas law. One of the things we need to note first is that they are not independent of each other. They influence each other. In the next video, we'll be going through examples in which we will essentially modify the ideal gas equation to examine other possible variables of a gas. However, for this video, we're just going to be focusing on the variables within the conventional ideal gas equation. So what are those variables? Well, pressure. As we discussed before, this is the force exerted by gaseous particles upon impact with the walls or other surfaces of a container or vessel, such as a cylinder, that acts as a system. This is calculated by dividing the magnitude of the force by the area over which the force is applied. And this gives us the force exerted per unit area. Now, outside of the ideal gas law, you could express this in newtons per square meter. However, we don't tend to use those units within the ideal gas equation. We'll go over those units in a bit. However, pressure gives you an indication of how often collisions do occur between gaseous particles and the walls and surfaces of a system, such as a container or cylinder. Volume. This is the size of the system that the gas can occupy. So this is the volume of the container or vessel. Amount, conventionally expressed in moles. This is the number of particles of a gas present in a system. And temperature. Absolute temperature, as we said before, this is the scale in which temperature is measured in Kelvin. And this is a measurement of the thermal energy that is converted into kinetic energy, which leads to the movement of gaseous particles. And at a higher temperature leads to more kinetic energy and faster particle movement. And if you remember from before, one of the assumptions we make about an ideal gas is that the temperature of the gas is proportional to the average kinetic energy of the gaseous particles. What this means is that if we have an increase in temperature, we're going to have a proportional increase in the average kinetic energy of the constituent gaseous particles. Okay, let's now focus on the units we're going to use for the variables in the ideal gas equation. Some of the variables can be expressed using multiple different units, whereas others can only be expressed using one unit. In this video, we're going to focus on the two most common unit combinations used for the variables within the ideal gas equation. For the two most common unit combinations, pressure is usually expressed either in pascals or standard atmospheres, simply known as atmospheres. Standard atmosphere is the unit of atmospheric pressure where we consider that 1 atmosphere, expressed as ATM, is the pressure of air at sea level. Now, a comparison can be drawn between pascals and atmospheres if we note that 1 atmosphere is equivalent to 101,325 pascals. Other units can be used for pressure, including torr, psi, bar, and millimeters of mercury. However, when it comes to the ideal gas equation, the two units most commonly used in chemistry and physics courses are pascals and atmospheres. Volume, two possible units depending on which of the two most common unit combinations you use. These are litres or meters cubed. We'll look at the two most common unit combinations in their entirety in a bit when we look at the ideal gas equation written down. Temperature, this is absolute temperature, so we only need to use one unit, and that's Kelvin. Then we have amount, which is expressed in moles. Now, earlier on in the video, I mentioned how in the next video we're going to be modifying the ideal gas equation to measure the number of gaseous particles present and express this as the actual number of molecules or atoms or ions. However, for the conventional ideal gas equation, we're going to stick to using moles as our unit for expressing the amount of the gas present in the system. Now, I've written on this slide that you may need to convert from one unit to another for certain variables to comply with the required unit combination. I would like to clarify that this is very likely. A common feature of questions involved in the application of the ideal gas equation is that you're given values for certain variables within the question, but they are given with the wrong units, and as a result, the numerical values are also incorrect for use in the ideal gas equation. This means you will have to convert the units and the numerical values to ensure that you can carry out the calculation correctly. We'll go through some common unit conversions next, but please remember to read any question you are given very carefully. Okay, let's look at some unit conversions. Now, I've included the equivalent values for 3 units that express pressure. 1 atmosphere is equivalent to 101,325 pascals, which is equivalent to 760 torr. Now, torr is still used in some laboratories. 1 torr is the pressure of air which supports 1 millimeter of mercury in a barometer at sea level. However, as I said before, pascals and standard atmospheres, or simply known as atmospheres, are the most used units for pressure in the ideal gas equation, and the most likely units you are going to encounter for pressure in an exam or a test. It is unlikely that you will have to convert from atmospheres to pascals. Most conversions involve going between different what we call SI prefixes, which express smaller or bigger versions of the same base unit. So some common examples you're likely to have to deal with include converting from kilopascals to pascals. Now, pascals would be the unit we would want to use for the ideal gas equation. However, it is very common for the value of pressure in a question to be expressed in kilopascals. So we would have to multiply that given value by 1,000 to produce the equivalent value in pascals. For volume, if you need to use meters cubed, you may be given a volume in decimeters cubed, which you must divide by 1,000 to give a value in meters cubed. You could instead be given a value in centimeters cubed, which you must divide by 1 million to give in meters cubed. If you're using the other unit combination, you would have to express volume in litres, and you may be given the volume in millilitres. To convert, you divide your given value in millilitres by 1000 to produce the equivalent value in litres. For amount in moles, typically, usually the only conversion you may have to do is from millimoles to moles, for which you divide by 1000. Temperature. Now, I personally have never seen a question where you're given the temperature in Fahrenheit. However, if this does happen, you must first convert this into Celsius by subtracting 32 before dividing the remaining value by 1.8. What is more likely to occur is that you're given the temperature already in degrees Celsius, and then you must convert that into Kelvin. To do this, you must add 273.15 or 273 if you're told to express this in three significant figures or without a decimal to your given value in degrees Celsius. The reason why this is the value you need to add is because 273.15 Kelvin is the equivalent of 0 degrees Celsius. So if you want to express a value in Kelvin rather than Celsius, you must add this value to the numerical value you're given in Celsius to have an equivalent value in the absolute temperature scale. Okay, so we've covered the 4 different variables that are in the ideal gas law and included as components in the ideal gas equation. However, there is a 5th component that is part of the ideal gas equation, a 5th value that is constant and brings together all 4 of the variables. This value is referred to as the universal gas constant, or the ideal gas constant, or simply the gas constant. 3 names for the same thing represented by the letter R. What this essentially represents is that providing temperature and pressure remains at the same levels in the system, if you were to experiment with 2 different ideal gases separately and the volumes of those 2 gases were the same, both gases would consist of the same number of moles of gaseous particles. Now, this is very much an assumption, and it's one based on what we call STP conditions, that's standard temperature and pressure conditions. This was proposed in Avogadro's law, one of those 5 laws that informed the ideal gas law. Essentially, Avogadro's law states that 1 mole of any gas in a system that has a temperature 273 Kelvin, 0 degrees Celsius, with a pressure 101,325 pascals, or 1 atmosphere, has a volume of 0.0224 meters cubed, or 22.4 liters. This means, for example, if we had nitrogen gas which contains diatomic molecules, so 2 nitrogen atoms covalently bonded together per molecule, and you also had carbon dioxide gas separately which contains covalently bonded atoms with different elements, carbon and oxygen, and they were present in STP conditions at a volume of 22.4 liters or 0.0224 meters cubed, both would contain 1 mole of gaseous particles, despite the molecules being completely different in terms of chemical structure. It's a nice way of bringing together different gases in this ideal world that is created in the ideal gas law. And we can use those values for the variables under STP conditions to calculate and to prove, so to speak, the value of the gas constant, the R value. We'll go over in more detail why this assumed constant is not likely to be applicable in scenarios involving real gases in the next video. However, for now, we're just going to accept this as a component of the ideal gas equation. So what is the actual value of the gas constant? Well, ironically, it varies depending on which units you use. Just like the variables in the ideal gas equation, the numerical value of the gas constant is different depending on which of the 2 main unit combinations you use for the ideal gas equation. Let's look first at what we're going to label unit combination 1. In this unit combination, pressure is expressed using pascals, volume in cubic meters, amount in moles, and temperature in Kelvin. With this combination, the value of the gas constant is 8.31 joules per mole per Kelvin. Now, where did joules come from? Joules is the unit for energy, and in this situation, it is representing both pressure in pascals and volume in meters cubed. Why? Joules represents pressure in pascals and volume in cubic meters because 1 pascal of pressure applied over an area of 1 cubic meter is equivalent to a force at a magnitude of 1 Newton per square meter also being applied over an area of 1 cubic meter. This is simply referred to as 1 Newton meter, which is equivalent to 1 joule. I know that sounds a little bit fiddly, but all we must know for the ideal gas law is that joules in the gas constant for this unit combination represents the units of pascals for pressure and cubic meters for volume. Okay, our second unit combination. Pressure is in atmospheres, volume is in liters, amount is in moles, and temperature is in Kelvin. The numerical value of the gas constant with this unit combination is 0.0821. Now the units within the gas constant for this unit combination are expressed as a fraction in a format that acts as a conversion factor, which is simply a way of cancelling out units relating to other variables that we don't want in our final answer and only leaving the unit for the variable we do want in our final answer. For instance, if we wanted to calculate the volume of a gas using the ideal gas equation, we would want to use liters for this unit combination and not moles, for instance, as this is the unit for amount. There are other videos on the channel containing examples of questions where conversion factors were used, links to which I'll leave down below. But please, please, please check the specification for your course to see which unit combination is required for the ideal gas equation and consequently which ideal gas constant you need. Some chemistry and physics courses don't require conversion factors and the correct unit is simply stated in the final answer without cancelling out erroneous units. This sort of course would tend to use the first unit combination in the previous slide, whereas the combination on the current slide tends to be used for specifications where the more regular use of conversion factors is required. Okay, so now we can see how the four variables and the gas constant are brought together to form the ideal gas equation. There's two sides of the equation separated by an equal sign. On the left side, we have pressure and volume, and on the right, we have amount in moles, the gas constant, and temperature. What this represents is that if we were to multiply pressure by volume, it would lead to a value that is equal to the result from multiplying the amount in moles by the ideal gas constant and temperature. According to the ideal gas law, the two sides of the equation must be equal. On this slide, we have unit combination 1. So pressure is in pascals, volume is in cubic meters on the left side of the equation, and on the right we have amount in moles, temperature in Kelvin, and the gas constant, which is in joules per mole per Kelvin. And there's also a reminder that the value of R to 3 significant figures, which tends to be the conventional number of significant figures used for R, is 8.31 joules per mole per Kelvin. Okay, and let's look at unit combination 2. So as you can see, the arrangement of the equation is exactly the same. P times V, pressure times volume, is equal to N times R times T, the amount in moles times the gas constant times temperature. The only difference is the units we're going to use. So pressure is in atmospheres, volume is in liters, amount is in moles, temperature is in Kelvin, and the gas constant, as you see here, we have liters, atmospheres, and moles and Kelvin, and it is presented as a fraction to allow it to be used as a conversion factor. And the value of R is also different. 0.0821 to three significant figures, and then we have that fraction arrangement, that conversion factor containing those units there. Okay, so now we know what the ideal gas equation looks like. However, in order to calculate a particular variable, we have to rearrange the ideal gas equation to make the variable of interest the subject of the equation. Now, to do that, we're going to have to use a bit of algebra, which I'll demonstrate in a bit. But the main rearrangements that you're likely to use are as follows. For calculating pressure, it's P for pressure equals the amount in moles times the gas constant times temperature divided by volume. For calculating volume, V is equal to the amount in moles times the gas constant times temperature divided by pressure. For calculating the amount in moles, it is N equals pressure times volume divided by the gas constant times temperature. And for calculating temperature, T is equal to pressure times volume divided by the amount in moles times the gas constant. Now, you can also, if you want to, prove the ideal gas constant, the numerical values of the gas constant at STP, standard temperature and pressure. And to do that, it is R equals pressure times volume divided by the amount in moles times temperature. And I'm going to do that in a bit. But let's have a look at how we actually rearrange the ideal gas equation to get these rearrangements. Okay, so at the top of the slide, we have the original ideal gas equation. P times V is equal to N times R times T. Pressure times the volume is equal to the amount in moles times the ideal gas constant times the temperature. Let's say we want to rearrange this equation to make pressure the subject. So let's write out the original equation again. P times V is equal to N times R times T. Now on the left-hand side of the equation, we have pressure, but we also have volume. Now in order to get pressure on its own, we got to cancel out volume. To cancel out a variable, we must carry out the opposite arithmetic operation to what we usually do when we use that variable. So we usually multiply by the volume in the original ideal gas equation. So to cancel volume out on the left-hand side of the equation, we must divide by the volume. And as a result, we can now cancel out volume on the left-hand side of the equation and leave pressure on its own. However, we must now carry out the same arithmetic operation we've just done to cancel out volume. We must carry out on the right-hand side of the equation. So we have the amount in moles times the ideal gas constant times the temperature divided by the volume. And as a result, we have a rearranged equation with pressure on its own on the left-hand side of the equation is equal to the amount in moles, N, times the ideal gas constant, R, times the temperature, T, divided by the volume, V. Let's do another one. Let's do temperature. Now, temperature in the ideal gas equation usually is on the right-hand side. Now, usually when we write out or rearrange an equation, we tend to like to have the variable of interest or the subject on the left-hand side of the equation on its own. However, if you have a situation where you have the subject or variable of interest on its own, but on the right-hand side of the equation, it doesn't really matter from an arithmetic point of view if it's on the right-hand side, as long as it's on its own. It's just conventionally we like to see the variable of interest or subject on the left-hand side of the equation. But as long as it's on its own, it doesn't really matter if it's on the right-hand side. So let's write out the original ideal gas equation again. So P times V is equal to N times R times T. To get T on its own, we must cancel out N and R, and because we usually multiply by N and R to cancel both out, we must divide by N times R, and we can now cancel N and R out on the right hand side of the equation, leaving T for temperature on its own, but we now must carry out the same arithmetic operation on the opposite side of the equation. So we have P times V, pressure times the volume, divided by N for amount in moles times R for the ideal gas constant. Let's now write out the equation again, but let's write temperature on its own on the left-hand side of the equation. So we've got T is equal to pressure times the volume divided by the amount in moles times the ideal gas constant. So it's T is equal to P times V divided by N times R. Okay, let's now prove the value of the universal gas constant, or ideal gas constant, or simply known as the gas constant. To do this, we're going to be using conditions under standard temperature and pressure, so STP, which are included in Avogadro's law. Now, you may be asked to do this in an exam or test. Sometimes they like to throw in a question just to test candidates' knowledge of how a theory came to be developed and why we accept this numerical value of the universal gas constant, a gas constant. Why do we accept this as the numerical value for this component of the equation? So for this slide, we're going to be using the first unit combination. So that's pressure is in pascals, volumes in cubic meters, amount is in moles, and temperature is in Kelvin. And we're going to be using the rearranged equation of R equals P times V divided by N times T. So that's calculating the gas constant by multiplying the pressure times the volume divided by the amount in moles times the temperature. And we're going to be using the values under STP according to Avogadro's law. Okay. So let's prove now the value of R using this unit combination. So we have, for pressure, we have 101,325 pascals. And we're going to multiply that by a volume of 0.0224 cubic meters. And we're going to divide that by an amount of 1.00 moles times by a temperature of 273 Kelvin. Now, if you put that in a calculator, the answer you get would be something along the lines of 8.31384,615, and the 384,615 would be recurring. So we would just go on and on. So it'd be 384,615, and then it'd be 384,615, 384,615, on and on and on and on and on. For simplicity, we're just going to be rounding this down to three significant figures. So 8.31, and then the fourth figure in this value is 3, so we're rounding down. So our answer, three significant figures, will be 8.31. Now, because this is the first unit combination we're using, we're not going to be using pascals, and we're not going to be using cubic meters for pressure and volume respectively. We're going to be using joules. So it is 8.31 joules per mole per Kelvin. Okay, let's now prove the value of R using our second unit combination. We're still under standard temperature and pressure conditions according to Avogadro's law. It's just that two of the variables now have different units, and as a result they have different numerical values in comparison to the previous unit combination. As I said before, this unit combination, you're more likely to use it if you're studying a course that requires the use of conversion factors to cancel out units you don't need for your final answer. Okay, so for this unit combination, pressure is 1.00 atmospheres, volume is 22.4 litres, amount is 1.00 moles, and temperature is 273 Kelvin. Our rearranged equation is exactly the same as the previous slide. It's R equals P times V divided by N times T. Pressure times volume divided by amount times temperature. Okay, let's prove the value of R using this unit combination. So we have, here we go. Okay, we have for pressure 1.00 atmospheres, and we multiply that by a volume of 22.4 litres, and we divide that then by an amount of 1.00 moles times a temperature of 273 Kelvin. And if we put that into a calculator, we would get an answer of 0.0820512, and from 8 to 2 it'd be recurring, so it'd be 0.0820512, 820,512, and we go on and on and on. For simplicity, we're going to be rounding to three significant figures. Quick reminder, if you have a value that begins with zeros, those initial zeros are not significant figures. You have to go along the value and to find the figure that is more than 0, and that is your first significant figure. So in this example, 8 is our first significant figure, 2 is our second significant figure, and then the 0 after that to be our third significant figure. The fourth figure is 5. 5 or more, we round up. 5 or less, we round less than 5, we round down. 5 or more, we round up. Less than 5, we round down. So in this case, we have a 3 significant figure value for R of 0.0821. And because this is the second unit combination, we're going to be given our units using our conversion factor fraction. So that's ATM dot L as a numerator, and then as a denominator, we have moles dot K for Kelvin for the temperature. When we're using this unit combination for calculating a variable, we're going to end up with a situation where we're going to be including this conversion factor in the overall fraction that we need to create in order to calculate the variable. We're going to end up with this sort of triple level sort of fraction arrangement, which is a little bit fiddly. However, there is a trick to overcome that, which we'll go through when we go through a practice question using this unit combination later on. Okay, let's now run through a practice question involving the first unit combination. What is the temperature in degrees Celsius of a sealed container containing 2.20 moles of nitrogen gas at a pressure of 110 kilopascals and a volume of 60.0 decimeters cubed? The rearranged equation we're going to be using is T equals P times V divided by N times R. Pressure times volume divided by amount times the gas constant. Okay, so the first thing I'm going to do is I'm going to go through the question again, and I'm going to identify which units are not compatible with the ideal gas equation, and I'm going to convert them and their numerical values. Okay, so immediately I can see here we are given pressure in kilopascals. We don't want kilopascals, we want pascals. And we're given volume in decimeters cubed. We want it in meters cubed. Okay, so we were given the amount in moles, which is fine. And for temperature, that is our variable of interest. But please note, we are asked to give that in degrees Celsius. Now that will be our final step. We need to convert from Kelvin to degrees Celsius. That will be our final step. But for now, we're just going to convert the units and numerical values for pressure and volume, so we can then put that along with the amount in moles and our gas constant into the ideal gas equation to calculate our temperature in Kelvin, before then we then convert that into degrees Celsius. Okay, so let's convert pressure first. So 110 kilopascals, and to convert that to pascals, we're going to multiply it by 1,000. So that's 110,000 pascals. For volume, we are given 60.0 decimeters cubed, and then we're going to divide that by 1,000 to give our answer in meters cubed, which is 0.06 meters cubed, or cubic meters. Okay, so now we've converted those two variables to the correct numerical values in units. We've got all three given variables with the correct numerical values and the correct units, and we've got a gas constant. We can now put those into our ideal gas equation, our rearranged ideal gas equation for T. So let's do T equals 110,000 pascals for pressure, multiplied by the volume of 0.06 cubic meters. We're going to divide that by an amount of 2.20 moles, and multiply that by our gas constant, which is 8.31 joules per mole per Kelvin. And we're going to get an answer to three significant figures of 361 Kelvin for temperature. Now we're going to have to convert that to degrees Celsius. So we're going to take that value, 361 Kelvin, and we're going to subtract 273.15. And that is the equivalent value in Kelvin to 0 degrees Celsius. So if we do that, we're going to get our answer, equivalent value in degrees Celsius, which is 87.85 degrees Celsius, which we've rounded to three significant figures is going to be 87.9 degrees Celsius. So our final answer to this question of what is the temperature in degrees Celsius of a sealed container containing 2.20 moles of nitrogen gas at a pressure of 110 kilopascals and a volume of 60.0 decimeters cubed, our temperature is 87.9 degrees Celsius. Okay, let's now look at a practice question using our second unit combination. What is the volume in litres of 6.00 moles of helium at a pressure of 1.80 atmospheres and a temperature of 45.0 degrees Celsius? Okay, so the rearranged equation we need for this question is V equals N times R times T divided by P. So amount times the gas constant times the temperature divided by the pressure. We only have to convert one unit for this question, and that's the unit for temperature. So we're going from degrees Celsius to Kelvin. So 45.0 degrees Celsius plus 273.15 gives an equivalent value of 318.15 Kelvin. Okay, so then let's put our values into our rearranged equation. So V equals 6.00 moles of helium multiplied by the gas constant of 0.0821 times the temperature 318.15 Kelvin and divide that by the pressure 1.80 atmospheres. Now, as I said previously, if we put our values into the rearranged equation as so, we're going to end up with a triple level fraction. So we've got our conversion factor, atm.L, as a numerator, and then we've got mol.K, moles and Kelvin, for our denominator for the fraction that is acting as the conversion factor. And then we've got another line to separate the numerator of the main fraction from the denominator of the main fraction. So we've got this sort of triple level arrangement. That can be a little bit fiddly when it comes to cancelling out units. However, there is a trick. The trick we can use to overcome this issue is that we can actually move the gas constant, but not very far. We can actually reposition it within the numerator of the rearranged equation. And the reason why we can do this is because the values in the numerator of the equation are being multiplied by each other. And it does not matter what order you put values in when you're multiplying, you're still going to end up with the same answer. So we can actually move the value of R one position to the right. So a slightly updated version of the rearranged equation is going to be V equals N times T times R. So we've essentially swapped the T and the R around, and we're still going to divide that by the pressure. So if we put in our values with our units into that slightly updated version of the rearranged equation, we have V equals 6.00 moles of helium times a temperature 318.15 Kelvin times a gas constant of 0.0821, and we divide that then by the pressure of 1.80 atmospheres. And now we can cancel out the units we don't want for our final answer. So on the top we have moles. We have moles here as well. Down the bottom we have Kelvin at the top and Kelvin at the bottom. And we have atmosphere here at the bottom and atmosphere here at the top. So the only unit we have left is litres, which is the unit we want for our final answer for volume. So we can now carry out this calculation, and we're going to give our answer to three significant figures. And so 6.00 times 318.15 times 0.0821 divided by 1.80, and we get an answer, three significant figures of 87.1 litres for our volume. Okay, let's do another practice question using the second unit combination, except this time the gas constant, the value R, is going to be in the denominator of the rearranged equation. How many moles of methane are present in a sealed container at a volume of 28.0 litres, a pressure of 1.60 atmospheres, and a temperature of 30.0 degrees Celsius? Okay, so the rearranged equation, when we write it out conventionally, is N equals P times V divided by R times T. So amount is equal to pressure times volume divided by the gas constant times temperature. However, we can update it, we can rearrange this even more slightly by having N equals P times V divided by T times R. So the slightly updated version is N equals pressure times volume divided by temperature times gas constant. We only need to convert one unit for this question, and that's for temperature. So we're going from degrees Celsius to Kelvin. So we're going to have 30.0 degrees Celsius. We're going to add to that 273.15 to get our answer in Kelvin of 303.15. Okay, let's now plug our values into this updated version of the rearranged equation. So we have a different color. There we go. So we have for n is equal to 1.60 atmospheres of pressure multiplied by our volume of 28.0 liters, and we're going to divide that by our temperature, 303.15 Kelvin, and multiply that by our gas constant of 0.0821. And now, because our gas constant is in a denominator, we have to flip the units within the conversion factor. So we've got moles and Kelvin as a numerator and atmosphere and liters as a denominator. That's just another little fiddly step that we have to remember. Okay, so let's now cancel out the units we don't want for our final answer. So we've got atmospheres on top and on bottom, liters on the top, liters on the bottom, Kelvin on the bottom, and Kelvin on the top. So the only unit we have left now is moles, which is the unit we want to include in our final answer. So let's now do this calculation. So 1.60 times 28.0 divided by 303.15 times 0.0821 to three significant figures is 1.80 moles of methane.